So we're going to begin solving problems in Chapter 17, Newton's Law. So this first problem, what we see here is we have a spool, and the spool is rolling on two rollers, A and B. The outer diameter of the spool is 1 meter, and the wire or rope that's being pulled off of the spool is coming off at a radius of 0.8 meters. And you can see the various geometries that are there. There's a tension that's in the, we'll just say in the rope, of 80 newtons. And notice we're given a K there. That K is at 0.65 meters is the radius of gyration. So we're also given mass, so we're inherently given the mass moment of inertia based on those two things. And so if you look just over to the side here, we have the free body diagram. Now note, when you do an exam, I expect free body diagrams all the time on these problems. If you get it 100% correct and it's missing, you'll be all right. You make the slightest mistake and the free body diagram's missing, you're probably down a lot of points, no matter what it is. So that's the free body diagram is important. So what do we have in there? If you look at the spool, it has weight, so that goes through the center of mass. It's very clear which direction that it's spinning in, so it's going clockwise here. We have the tension, and these are the support forces. That would be then going up through pointed up towards O, which is also the center of mass for the thing. All right, so we want to solve this thing. So if you look at what's being asked for, we have acceleration and force. So those things tend to go together for Newton's law. So we'll start solving this thing. And so there's basically three equations we can do. Sum of forces, that'll be x and y, and a sum of moments, which we'll do about the center of mass. So relative to x, mass times acceleration of the x along the x, we know that's 0. This thing is not translating. It's not moving up or down side to side. So this is going to be 0. So going to our free body diagram, we have this one going NA sine 15 in the positive x. This is going in the negative x. And that's all there is. Solving, that tells us the two support forces are equal, which stands to reason. If you were to take a moment to look at this problem, just think about it. In the y, this again has to be 0. All right, so we have these two going up, 60 coming down, and the 80 coming down, or 60 times 9.81. And that'll be 0. Okay, so if we look at this one, and the equal 0 part is missing here, so we'll just add that in. Okay, and there that is. So we can solve for NA off of that. So we were to find NA and NB, so we can solve for those right away. Taking the moments about the center of mass. This does nothing, this does nothing. They're all pointed through G, or C, the center. So this provides the only moment, and so that would be 80 times 0.8. All right, it's going clockwise, so that's negative, so we can just write that directly. Ig is the mass times the radius of gyration squared, and then we have alpha, which will obviously be going in the same direction as those. And so we can solve for alpha, and we get 2.52. This would be radians per second squared that's missing. And NA and NB at 346 newtons. So our next problem. The next two problems actually that we're going to deal with a rather well-known class of problems, and they're called tipping or slipping problems. So the goal is to figure out what will be the motion. All right. So is the problem as it looks to move, will it be slipping or will it be falling over? All right, so we want to find that we have a bottle, 2-pound bottle. It's 3 inches wide. The center of mass of the bottle is up 8 inches. It's on a belt where mu(s) equals 0.2, the static friction coefficient. Now our question is how fast can we move this belt along without having a tip or a slip? And so the question is to find that limit is which one happens, tip or slip first. So we have to figure that out. What makes this problem complicated? There's two things we have to be concerned with. First of all, we got to look at mu(s). mu(s) and mu(k) are different, okay? We have, in friction, you have mu(k), the kinetic friction coefficient, and that describes the actual friction force when something is sliding. It gives us the real force. mu(s) doesn't do that necessarily. So if you think about something, if you have a box and it's just sitting there, what's the current friction force? 0. So there's a mu(k), there's a mu(s), and so this is if it's not moving, this is the maximum available. So you have a force N. So if this isn't moving, the available friction force is mu(s)n, but you only get as much friction force as needed. So if you start to apply a force to push it, then there will be a friction force that will oppose it, and it will build up to a maximum of mu(s)n, mu(s) times the normal force. We'll put that in here. And once you start to move, the friction drops down to mu(k) times n. All right. So when you see this here, you're tempted to say, well, the friction force is 0.2 times the normal force. Not necessarily. That's that helps you know the maximum available. The question is how much is available. So it's makes it a little more tricky. The other thing you got to be concerned relative to tipping is what is the normal force? Well, as this thing starts to accelerate, all right, this thing will start to kind of lean. All right, so you tend to put the normal force in the center, pointing up to the center of gravity. But what really happens is it leans. And so that normal force is going to be moving back. As this thing accelerates forward and this thing wants to lean like so, the normal force is going to move back. The problem is when the normal force moves back to the point that it is outside the bottle, that's when this tips. So the question is, where's the normal force applied? Again, it's not quite clear. So we have two limiting conditions. When the normal force gets to the outer edge of the bottle, that's the tipping limiting condition. And when friction force gets up to mu(s) times n, that's the slipping limited condition. So we've got to take both of them to those points. All right. If you're having a hard time imagining the normal force moving back, I would just comment that one of the things I did with my son when he was in 8th grade, I took him to New York City, and I played a game with him. We had a wonderful trip. We went all over and saw things in New York City. And one day we went to the Statue of Liberty, and we came back in. We took the subway quickly back up to the hotel so we could get ready because we had going to the Yankees game that night. Anyway, so when we're on the subway, and the cars look, say, something like this, okay? If you're inside, dangling in the these cars aren't very long, and when you think about city streets, so there's a city street. If a subway train, which is underground, is going like this, if it has to turn at full speed like that, okay, to go down another street. This is all underground, but the nature of the turns here are really, really sharp. And these things run on electricity. There's no diesels down there pulling these things along, so they have really, really high torque. So here's the game when you get on a subway, is there were seats that we could have taken, but I went to my son and said, here's what we're going to do. We're going to basically, you have a car, and you got seats like so. Well, actually, no, it was more like this. Kind of seats along the wall. So you had the space in here. And so the game is to stand and see who would be the first person to fall as the subway's whipping around. And if you've done this before, here's what happens: as the subway pulls out of a station, say going this way, the acceleration is really, really strong, just like we have for this belt here. And so what you need to do is you need to, if you're standing here, is you got to put a lot of weight on this back feet, your back feet, because if you're even, this thing can accelerate and you'll fall right over. Okay, that's the same thing that's happening here. As this speeds up, the normal force which is supporting this has to kind of come to the back, and to support it, if it had to go be outside the bottle, which is physically impossible, bottle's tipping over. All right, so that gives us a little perspective on this problem. So basically, when you do these problems, what you tend to do is you assume one of them happens. So in this case, I'm going to assume slipping occurs first. So I'm going to take this thing to the limit that would be expected based on friction. And we'll see if we reach a contradiction or if we have to go back to tipping. So you usually wind up just assuming one happens and finding the limit and then flipping back. All right. So we need a free body diagram. That's right here. So here's my caricature of the bottle. So here's the center. The bottle weighs 2 pounds, so that'll be 2 pounds going down through G. Here's the center line of the bottle. And now notice the belt is pulling us along this way. So friction. Why does the bottle move? Because friction is actually driving it forward. Okay? You tend to always think friction opposes your motion. In this case, it's causing it. All right? A little bit different. And then here's the normal force, which is going back some distance x to stabilize the whole thing. All right. So we'll start looking at our first set of equations. And so summing the forces in the x, mass times acceleration, is simply going to be driven by the force of friction. I'm calling that FB. I have no idea why I said FB, but it is what it is. 2 divided by 32.2 AGX. Okay. Summing the forces in the y, n minus 2 equals 0. This thing isn't moving up and down in the y-axis, so normal force is 2 pounds. That was kind of obvious. And in general, if we sum the moments about G, what we have is the friction force, okay, driving it forward. If you look relative to G, that's actually producing the tendency to want to tip. Okay, so we have FB, it's 8 inches up, so in terms of feet, that's 2/3. So that's what we see, it's 2/3 of a foot. That's the counterclockwise one. And then the clockwise torque that wants to compensate for that is n times this x. So those are the 3 basic equations that we have. All right. So prior to slip, what do we know? We must have maximum FB. Okay. So the maximum force of friction, n equals 2, is 0.4 pounds. Okay, 2 times 0.2. And so if I stick this 0.4 into here, that would say that the acceleration is 6.44 feet per second squared. Okay, so there's an answer based on that. But the problem is does that work? All right, so now we're going to we're going to go to this problem. So 2x equals FB times 2/3. So we'll stick in our 0.4 pounds for this and solve for x. We wind up with x is 0.13 feet, which is 1.6 inches. So if we're just at the point of tipping, the normal force to support this is outside of the bottle. So it's already tipped. So bottom line answer, that doesn't work. So that tells us, okay, we know we're going to tip. So that says if we're tipping, we're going to go back up here. And we're going to say, okay, since we are tipping, we know the normal force is right on this back edge. So that tells us when we go through these equations here, we know x is 1.5 inches. That will tell us what the force of friction is. then that in turn will tell us, we'll put that into here, and that'll give us the acceleration. And that's exactly what we see. Knowing the x, that determines the force of friction, which is of course going to be less than the maximum available 0.4. Sticking that into the x equation, we get the available acceleration is just over 6 feet per second squared. So there's that one. So we're going to stop right here. I'll be starting another video in just a moment. We're going to do one more tipping and slipping problem, and I'll see you then. Bye now.